Hello, I'm Hilltop, and welcome to a very in-depth look at how I extract 2D graphics from PS1 and PS2 games. This video will primarily focus on 2D texture identification and extraction, and in order to get to that, we're going to have to talk a lot about the general computing theory behind 2D graphics. Now, what's not going to be in this video, unfortunately, is going to be talking about how to get past file systems and file compression. That would simply be too much to put into this video, and that wouldn't necessarily only cover 2D graphics. This video is really focused on identifying graphical files themselves. Now, this video will be broken up into two sections. The first is the beginner section. If you're someone who's completely new to programming or don't know any programming at all, and you just want to know what tools you can use to very easily rip images from games, that'll be that section for you. But in part two, which is going to be the most of the video, we're going to talk about how we actually analyze files and study documentation and how to create our own programs in order to extract images. Now, the beginner section. We're going to talk about how we dump files from a game and how we're going to feed those files to a graphics program. And really, we're just going to hope for the best, because if something doesn't work out, there's really not much we can do without any programming knowledge. And these techniques will definitely work on some games, but are absolutely not guaranteed to work for all games. Now, the first thing that we have to do is to get the actual files themselves. And luckily, this is pretty easy, and there are a lot of tools that we can use to help them out. What we want to extract files from are the disk images. These are .bin files for PS1. Usually there'll be an accompanying Q file. And on PS2, these are ISO files. Now, to look at what files are on the disk, we're going to do something called mounting. We're going to mount the image file. On Windows, it's very easy. All we do is right-click the file. We right-click the Q for PS1 and the ISO for PS2. And we select Mount. This is on Windows 11, by the way. And we basically just hit OK on whatever comes up. And then we'll have a drive on our system that has all of the game files. In this case, it went to drive V. When it comes to images, on PS1, we're looking for .tim files, and on PS2, we're looking for .tm2 files. It's not guaranteed that we'll find them, though, but if we do, it makes our job very easy. We can open up the files in a program called Noesis. It's very simple. All we do is we just select the files that we identified earlier, and they should show up as an image. After we've done that, we can use the export media function and export our files as PNGs. And that's all there is to it if we found TIMs. But what if we didn't find any TIM files, and it's actually quite likely that that's going to be the case? Well, we don't need to panic just yet. The images could be stored inside of other files, or they could be renamed and not TIM files necessarily. What we can do is, for PS1, we can open up the bin file in a program called jpsxdec. Among other things like video and audio, it will identify the files that contain TIMs, and we'll be able to export it from that program. On the PS2 side, we can use a program called Game Graphics Studio. All we do is open up our ISO file, and then the contents of the disk will be listed here. We right-click one of the files that we suspect will have a graphic in it, and we go to search for graphic files. Images that appear will appear in this section here and down here. And you might need to mess around with some of the options in order to get the image to look correct, but images should appear if they exist in TIM2 format. And from there, it's as easy as saving them as a PNG by using this button. Now, there are other tools that you can use if for some reason one of the other ones didn't work out. Tim to View has a very simple interface. You literally just drag and drop files into it, and it will identify TIMs for PS1. Rainbow is a tool specifically for opening TM2 files. So if they're not exactly TM2 files that the game's using, they won't appear. You will also need to mess around with color palettes potentially in order to get the image to look correctly, and you can do that by selecting these buttons here and here. There are many, many limitations to using these tools. First of all, nothing might appear at all. It's not guaranteed that a game will use one of those formats that those programs can handle. And even if they are using those, it's possible that many different issues can occur, such as wrong colors in different parts of the image, the transparency might be wrong, the horizontal scale might be wrong, images might look squished, and images might look totally corrupt. And by the way, these are all real examples that I've encountered when trying to use some of these tools. And unfortunately, that's basically all we can do for now. I said that in the beginner section, we're going to basically have to hope for the best. There's no guarantee that any of these tools will work. You might be left with nothing at all after running your game through these tools. In order to make any more progress, you will require some programming knowledge. You will have to look at files in a hex editor and understand hex and code and all sorts of programming fundamentals like that past this point. So let's get into it. Let's get into the advanced section. This is what I've been waiting for. So we're going to talk a lot about graphics theory. We're going to talk a lot about how we can study the SDKs provided by the console manufacturers in order to understand how graphics work. We're going to be able to identify graphical files using those concepts. And we're going to learn how we can use that knowledge that we have gained from the known formats in order to extract graphics from proprietary formats. And that's when the real fun begins. By using these techniques, we can greatly, broadly increase the amount of games that we can rip textures from. But games have a habit of throwing many, many different walls, many different challenges. So nothing in this video is going to be a silver bullet for how to extract a texture. There are literally infinite different ways that a game can package their textures together and reference it and do all sorts of things like that. So let's dig in. What is a 2D graphic? Well, when it comes to computers, and especially when it comes to video game consoles, a graphic is any file that a computer can rasterize or map onto a 2D grid of pixels. What does that mean? It means that an image, in terms of a video game console, is just a list of numbers. A list of numbers where a number or a group of numbers corresponds to the color of a pixel. And in the very most basic example, we have this graphic right here of this Pac-Man Ghosts. As you can see, a number of 0 indicates a white pixel, and a value of 1 indicates a black pixel. So we can see that the number of the pixel corresponds to what color it is. Now, we said that the numbers correspond to a color, but what is a color? What does it mean for something to be a color when it comes to video game consoles? Well, colors tend to have 3 and sometimes 4 components when it comes to these systems that we're talking about. They're usually a list of numbers that contains a red value, a green value, a blue value, and at times an alpha value. And that alpha value is another way of saying a transparency value. Here is a certain color, this shade of purple. It's the same color taken at different alpha values. Here it is with an alpha value of 0. You cannot see it because it's completely transparent. At an alpha value of 0.5, it's fainter, but it's still there because it's at 50% transparency. and at an alpha value of 1 or 100%, we can see the color as it's basically meant to be seen at full opacity. Now, the way these values get added is not like mixing paint together. These numbers get added together additively according to light mixing rules, which you might have learned maybe in elementary school. So that means that the color white contains all of the colors of the rainbow. And the rainbow in our case is red, green, and blue. So a value of a white color is represented by maximum red, maximum green, and maximum blue. In this system that I've just written up right here, the maximum value of a color is 255. That's a very common number that you'll see a lot, and that's why I chose it. You can get white light by adding blue light, green light, and red light together. And following those rules, black is the absence of light. So black contains no light, so it has a value of 0 in all of its components, red, green, and blue. Now, red is obviously maximum red, and then 0 and everything else. Green is maximum green, and 0 and everything else. And if you add red and green together, you don't get brown, you get yellow. Because we're adding with light mixing rules and not paint mixing rules. We're adding the colors additively and not subtractively, which is how they refer to it as. When it comes to computer graphics, a word that comes up a lot is color depth. Color depth for an image refers to how many unique colors that an individual pixel can be colored. That number comes from how many bits are used to hold the data for each pixel. The number of colors can be determined using the formula 2 to the power of the number of bits used to hold each pixel. For example, in a 1-bit image, for example, this image of Pikachu here, 1 bit, if we use our formula, 2 to the power of 1 is 2. So this image can be, so pixels in this image can be any of 2 colors. And here we can see it's obviously white and black. This image of Mario is a 2-bit image. That means that any pixel can be colored any one of 4 different colors. As we increase the color depth, you can see that the images can be much more detailed. We can have a much richer palette of colors. And when we get to 15-bit, it's hard to tell that it's even a limited color palette at all. The 8-bit image is very rich, but you can still see artifacts like color banding in the gradients. With the 15-bit image, it's hard to really make out the fine artifacting. The gradients look very smooth, and that's kind of a hallmark of high color depth images. The gradients are very smooth. Of course, as you increase color depth, you increase the amount of space, the actual memory that the graphic occupies. So that's why we tend to see low color depth images in very old consoles and higher color depth images in relatively newer consoles. We said that the values of a pixel, the number assigned to a pixel, can refer to a color. But how does it actually do that? Well, there's something called a color palette that tells us how to get from a number to a color. For example, in this image, depending on which color palette we apply to it, we can end up with a different image. We can end up with either Mario or we can end up with Luigi. Now, the underlying image is actually the same. The only thing we changed was the color palette. The only thing we changed was the mapping of numbers to colors. For example, a pixel that is numbered 0 is this light gray color in the, let's say, the original data without any color palette applied to it, although I have applied this arbitrary palette just to visualize it. As you can see, 0 corresponds to transparent pixels with both Mario and Luigi, but pixels that have the value 1, for example, become red with Mario, but white with Luigi. You could think of the pixel values, the numbers assigned to each pixel, as an index for a color in a corresponding color palette. And that's how we get a colored image from a list of numbers and a color palette. But actually, it's entirely possible to represent an image without using a color palette. In this case, we can, instead of storing the index of a color in a color palette inside of a pixel, we can just put the entire color inside of the pixel. The reason we don't see this very often with older consoles is it takes up much more space than using a color palette. Instead of holding basically one number in a pixel, you have to store up to 4 numbers inside of a pixel. So much more space being taken up by these kinds of images. In this example here, let's say we had this pixel that is red. In order to store this pixel, we have to store the red value, the green value, and the blue value, and the transparency value, the alpha value, inside of that single pixel. And we have to do this for every single pixel in the image. I will be referring to this kind of image as a direct color image. I'll be referring to the previous kind of image as a paletted image. They're two very distinct types that we'll have to deal with on PS1 and PS2. A very important detail is that the colors in a color palette and the pixels in a direct color image share the same format for each system. So that means for PS1, they are the same, and for PS2, they are the same. But, they're distinct from each other. PS1 is distinct from PS2. On PS1, the colors are stored at like this. They're stored as 2 bytes, with the lower 5 bits storing the red value, the next 5 bits storing the green value, the next 5 bits storing the blue value, and then there's 1 bit left over, which is called STP, or semi-transparency processing. And that bit sort of represents the alpha value, but it's not exactly, and we'll get into that later. On PS2, direct color pixels or colors in a color palette has this format. It's stored as 4 bytes, with the first byte being red, the next byte being green, the byte after that being blue, and then the next byte being the alpha. Now, important to note that on both of these systems, both of these systems are little endian, so they store the least significant byte first. Now, keep that in mind. Also, some programs will refer to little endian as Intel versus big endian being Motorola, so you just need to keep that in mind when using different tools. So we said that an image contains all of the pixel values, and as well as the color palette. But what order are they stored in? Well, it's in this order. The pixels are stored starting from the top left and then going across, and then going to the next line and going across, and then repeating that pattern until the entire image is stored. You'll notice that this kind of only applies to rectangular images, and that's almost entirely what we're going to be working with. We're going to get a little bit into like rectangular images later, but in general, an image is going to follow this format, and it's going to be stored in this order, with this kind of zigzagging across each and every single line. Now, the color palettes are stored kind of as you would expect for PS1, in that the color value that corresponds to 0 is the first one, and then 1 is the next one, and so on. That's how it is on PS1. But there's kind of a weird ordering going on in PS2, and we'll get to that later. We're finally going to start looking at images in a hex editor. I know this was the moment you've been looking forward to. So here's just an example image, the image of this like egg graphic right here. I have the color palette right here and the actual pixel data for the image right here.
We found 19 different blocks of numbers like this one.
What do they mean?
They could mean anything.
Now this image is 4 bits per pixel, which means it has 16 colors, and the colors themselves are 15 or 16-bit, kind of depends how you look at it. This is a PS1 image. The size of the color palette, because there are 16 colors and there are 16 bits per color, that gives us 32 bytes after we divide by 8 bits per byte. So here's a little formula for finding the size of the color palette. And the size of the actual pixel data, we take the bits per pixel, multiply it by the width of the image and the height of the image, and then we divide by 8 bits per pixel. And this is a 32 pixel wide by 32 pixel tall image. So we take 4 multiplied by 32 multiplied by 32 divided by 8, and we get a complete size of 200 bytes. That's actually 200 in hex. So I should actually fix that. So there we are. It is actually a 512 byte size image looking at just the pixel data. And like I said before, PS1 and PS2 are both little endian, so you always need to keep that in mind. What's interesting looking at the data itself is that you can kind of see the shape of the egg looking right at the data. You can actually kind of see the shape. And even in this kind of like ASCII representation of the data, you can see the shape as well, although it's very elongated. You can see why, though. You can see that all of these numbers that are 0 correspond to the first color in the color palette, which is actually transparent. These black pixels around the egg are actually supposed to be transparent. And so you can see that they're all 0 when it comes to the actual data itself. You can kind of see that correlation. Of course, the only reason that the image lines up in this way, where the data looks like the actual image itself, is because the width of the image actually corresponds to the width that we have set up in our hex editor. This is a 16-byte wide hex editor screen that we have going on, 16 bytes wide. And if you look at a single line of data in this image, it's going to correspond to 16 bytes because it's 32 pixels wide, but it's only 4 bits per pixel. So we take 32 divided by 2 and we get 16. So 16 bytes per line, essentially. For this example, I just set it up that way because you can easily see the relationship between the data if it matched up perfectly like that. Something you're going to have to get used to seeing when looking at images in this way is that a lot of images are going to look squished horizontally. And why is that? Well, it's because each pixel only takes up a single hex character, aka 4 bits. You know, a single byte is 8 bits, so half of a byte is 4 bits. So there are 2 pixels per byte. So there's a general rule where the lower the pixel depth, the lower the image depth, the color depth, the skinnier the image is going to look when looking at it in a hex editor. If the pixel depth is higher, it's going to look wider. So there's that relationship going on between the hex and the actual image and the color depth. Now it's time to introduce the concept of VRAM, or video RAM, I think it's actually called. So to render an image on a PS1, there's actually a whole kind of pipeline that the file has to travel. It has to start on the disk, and at some point from the disk it'll be loaded into RAM, and then from RAM it'll be loaded into VRAM. Now, we're going to talk all about VRAM in the next section, so don't worry if this looks a little bit scary right now. It'll make sense later. Now, the VRAM has a special part of it called the frame buffer, which is where a graphic will be sent. And then after it's on the frame buffer, it can finally be outputted to the TV. And that step we don't really care about. That's kind of determined by hardware and kind of all sorts of weird, scary emulation stuff. We're not going to care about this step, the final step right here. What we care about basically is how things get loaded into VRAM and how they get sent to the frame buffer. After it's on the frame buffer, we don't really care. VRAM is a concept that is specific to the PS1, at least in terms of this video, because the PS2 has what's called unified RAM, where all of its RAM can be used as the VRAM, which is actually a very nice feature for developers to not have separate RAM and VRAM. But the PS1 does have separate VRAM, so this section is kind of going to be all about PS1. VRAM is essentially one big buffer, one big block of memory that we can view as one big image. And that image is 1024 pixels wide and 512 pixels high if we're looking at it in 15-bit color depth. This image is taken while looking at it in 15-bit color mode. So this image is 1024 pixels wide and 512 pixels high. If we were looking at it in a different color mode, it would look either wider and the colors would be different, or possibly thinner if we were looking at it in a higher color depth mode. Now, the only part of this image, the only part of VRAM that looks normal to us is the frame buffer. Because in order to render a frame, in order to send an actual image to the television, all the graphics that make up a frame have to be converted to 15-bit / 16-bit, kind of depends how you look at it, and it has to be assembled onto the frame buffer. So we said that graphics have to go to VRAM, and then it gets sent to the frame buffer. Well, when it's in VRAM, it's in its kind of more condensed state, if it's a paletted image. And it gets basically inflated before it gets placed onto the frame buffer. We'll talk all about how that works. So here are the frame buffers. There are 2 of them. Now, the reason that there are 2 of them is actually kind of interesting. So in order to maintain the video signal without flickering, basically the system needs to be able to render or display one frame buffer while it works on assembling the next frame buffer. So basically each one represents one frame of the video signal, and it'll be displaying one frame while it builds the next frame in the other buffer, and it trades that role between the 2 buffers as it goes on. So VRAM also contains all of the pixel data for all the images that it needs to display, and now that includes 2D images as well as textures for 3D models. It also does include those. It also contains all of the color palettes that are used in whatever scene is going on in the game. Now, the frame buffers look pretty normal. It looks like the game, at least when we view it in this color mode. But as you can see, the pixel data does not. It looks kind of weird. The colors look off and it looks squished. That is because we are viewing it in the 15-bit color mode. And these images, as they're being stored in VRAM, are not in the 15-bit color mode. They could be in 8-bit mode. They could be in 4-bit mode. They could be in any kind of mode, really. As we saw before, different images can have different color depths, but they have to be converted into 15-bit to be rendered on screen, to be put onto the frame buffer. So say we wanted to take a single image, a single 8-bit per pixel image, and we wanted to put it on the frame buffer. Well, in order to do that, we would need to combine it basically with the color palette, the associated 16-bit per color or 15-bit per color. Depends how you look at it. The reason I always say it depends how you look at it is because, as we said before, the color mode of the PS1 doesn't really have an alpha channel. It just has that one bit. And in some contexts, that bit matters. and in other contexts that last bit doesn't matter, but we'll talk all about that later. So say we wanted to put the first pixel of this image into the correct position on the frame buffer. Well, what we would do is we would go to the first byte of the pixel data, because this is 8 bits per pixel, so we look at the first 8 bits, and whatever that value is, let's say it has the value of 40, we would go to that would mean we go to the 40th color in the associated color palette, and then we would copy that color onto the frame buffer in the first pixel. And then we would repeat that process for every single pixel in the image. We would take the value, we would interpret that value in the pixel data as an index, the index of a color in the color palette, then we'd copy that 16-bit color over to our 16-bit per pixel image. So the color palette has the same color depth as the frame buffer. That's very important. They are on the same wavelength, basically. But the image is not on their wavelength. It's on a different format. So that's why it has to be converted in that way. It has to be kind of sanitized, going from something that's less than 16-bit to 16-bit. And that's the way that it does it, it looks up colors in the color palette and uses those same format colors to put into the frame buffer. In fact, take a look at this. This is the game running in an emulator called PCSX Redux. And I have the VRAM viewer open, so you can actually see VRAM animating live as the game is being played. So you can see that in the normal mode, you should be well accustomed to it, that the frame buffers look normal, and the rest of VRAM looks, well, it looks weird. But what if we change the mode that we're viewing VRAM in? See, we're looking at it in 16-bit mode. What happens if we change it to 8? Well, suddenly, the frame buffers look very weird, but a lot of this data, a lot of the images look normal. In fact, if you look at the image that we were talking about earlier, the 8-bit image, suddenly the 8-bit image looks normal. Now, it doesn't look correct because the colors are, it's just being assigned basically a grayscale color palette, because this VRAM viewer doesn't know which parts of VRAM should be viewed with which color palettes, but it looks relatively normal because we're looking at it at the correct color depth now. Now we can go even further and look at VRAM in 4 bits, which makes things even wider. But as we can see now, some of these images that were 4-bit color mode look normal now. And now the 8-bit one also looks wide. Very, very interesting, don't you think? I didn't mention it earlier, but the entire reason that games will use lower color depth images is not just that it takes up more space on the disk to use higher color depth images, but also, as you can see, VRAM is very, very small in the grand scheme of things. It can only really hold so many images, and so it's kind of an optimization. It's a limitation of the system that you try to get past by using lower color depth images, by trying to fit as many graphics as you possibly can into this tiny little space that you have. So you see games do all sorts of weird things to fit all their graphics into this little box. Now that we know how an image is defined and how it has two very important parts that we want to look at, the color palette and the image, how does the TIM image format work? So let's take a look at how TIM works on the PS1, the standard format. Well, we have the actual SDK, the documentation that tells us exactly how it works, provided directly by Sony from their developer tools. According to the official documentation, it has 4 distinct sections to the file. Now, reading this over here, the introduction, we learn a few things that I mentioned a bit before. The VRAM is based on 16 bits. We talked about that and how it's usually seen in, we usually look at VRAM in 15-bit mode. But it also says it goes all the way up to 24-bit, and we didn't really talk anything about that. That's because the VRAM only goes to 24-bit mode when it's rendering a video, when it has a full motion video happening. And it's very rare that any graphics are going to be in 24-bit mode on PS1. I think the only time it ever really would be is if it's a graphic that's meant to appear on top of a video, on top of a full motion video, and that's extremely rare. So it's highly unlikely you'll ever see 24-bit images. Here we have the image that I showed you before, the image of the egg. And so it starts with the ID. The ID is composed of one word. Words on the PS1 are 4 bytes long. And so it says that basically it's just the number 10. It starts on the low byte. There's 10, the ID, and the rest of it is 0. This is basically always how a TIM is going to start off, with this little ID header that it uses to identify this file as a TIM. After the ID section comes the flag section, which tells us some information. But it also tells us that only the first 4 bits are actually used. Only the lowest 4 bits are actually used. The first 3 make up something called P mode, and the 4th bit is the CF. The first 3 bits, the P mode, is what pixel mode, basically the image mode that this image is in. So for this egg image, we said that this was a 4-bit image, 4 bits per pixel. So it's 4 bits per pixel, and it has a CLUT. What is CLUT? CLUT is color lookup table, and is the more technical word to use to refer to a color palette. And that's what we're going to use going forward. The CF bit tells us whether there is a CLUT included in the image or not. So this is the format of the pixel section for P mode, and then CF is just whether or not there is a color palette included with this image. Now you might be wondering, why do we need to manually specify if there's a color palette or not? Doesn't there have to be one for an indexed image? An image that's not direct color? Well, sort of. There sort of has to be one, but there doesn't need to be one within the TIM. We'll talk a little bit about why that's the case. It has to do with a limitation of the TIM format itself, and the idea that TIMs, while usually representing graphics, don't always do so in such a clean and helpful manner. There's something else going on, but for now, we'll just treat this as is, basically. It's also very ominous that there's this mixed pixel mode. Explains it a little bit up here. And it just says that different types of data can be intermingled. And that's not a very helpful explanation when it comes to trying to extract the image. It's another one of those little limitations of the format that we'll talk about later. So after the flag, we have the CLUT. And the existence of this block of data depends on the CLUT flag that we saw earlier in the flag. So the CLUT has this format. It starts with something called bnum, and that's just how big the block is. Just how big this little block of data is that I've highlighted here. After that, we have dx and dy, and these are coordinates. These are x and y coordinates for where this CLUT is going to go and live in VRAM. So exactly where can we expect to find the data of this color palette in VRAM? This is where it ends up. So the game is going to load up a TIM. When it opens it in RAM, it's going to read this header, and then it's going to send this data to VRAM at these coordinates. Then we have width and height. And it's a little weird to think about width and height when it comes to a color palette. Like, why does a color palette have dimensions like this? Well, you can think of color palettes as actually being images themselves. You can think of a color palette as being just like a sequence of colors, of single pixel colors in a sequence. And because it's an image, technically it takes up the same area as an image, and it's technically a series of pixels. You can have color palettes that aren't linear like this, exactly linear. It could be rectangular. You can have a color palette that is rectangular as well as just a straight line. So that's why it has these dimensions here, because this determines how this data is going to be sent to VRAM, exactly which pixel it's going to occupy. And then after that, we have the actual color palette entries themselves. So for this color palette, the color palette for the egg image, it has a binum of 2C, and it has some coordinates that it gets loaded into VRAM. And then the width and the height, it has a width of 10, which in decimal would be 16, because there are 16 colors in this color palette, and a height of 1. So this works out exactly as we expect it to. So, and then we have the actual color palette entries themselves, the actual colors in the color palette. As we said before, the colors on the PS1 has this format, basically what we call RGB 555. 5 bits red, 5 bits green, 5 bits blue. Then we have what we kind of hinted at earlier, way earlier, the transparency control bit, STP. Now it's a little complicated to explain what this does, but I'll give it a try. Because we only have one bit to control transparency, we can't really have proper alpha values. So how do we have, proper transparencies in an image? Well, there's a bit of funny business going on. Basically, the system itself at runtime can choose to render an image with translucency processing on or off. If it's off, things are pretty simple. We reserve 0 STP of 0 with 0 red, green, and blue to be our transparent color. Of course, 0, 0, 0 for red, green, and blue can also be black. We can also interpret that as black. So we use the STP value of 1 with 0, 0, 0 to represent black in that case. So we can represent either black or purely transparent by flipping the STP bit. When the translucency processing is off, in every other case, flipping the bit does absolutely nothing. According to this table, if you have something between that's more than 0, 0, 0, flipping the bit does actually nothing. It goes from not transparent to not transparent. So when translucency processing is off, there is no alpha value being rendered other than full opaque or fully transparent. And fully transparent is represented by pixels that are 0, 0, 0, 0, like this. But the PS1 can render images that are only partially transparent, partially opaque and partially transparent, what we call translucent. And that's when the real magic happens. So when translucency processing is on, suddenly there is a difference between colors that have the bit flipped, the STP flag flipped. So suddenly, having the flag on results in pixels that are semi-transparent. And we'll talk more about what that means. And now we get to some of the dark and dirty business of TIMs. The reason it's dark and dirty is because just by looking at a TIM, it's actually impossible to know for certain how to correctly rip an image. It's actually impossible to correctly extract an image because there's no way that we know for certain what an image actually looks like by reading the data in the TIM. This translucency processing with semi-transparency and whatnot is all handled at runtime by the game's code as it's running. On top of translucency processing being either on or off, there are actually 4 different modes that the game could be using to blend opacities, basically. how to blend an image with its background when it's only partially transparent, when it's semi-transparent. So semi-transparent images, semi-transparent pixels in an image, will inherit color from the image itself and the background of wherever it's placed. But the way it does so can vary depending on these 4 different blending modes that it could use, and it can change between at runtime. So here are each of the modes for semi-transparency processing and how they work. So we have mode 0, which is a 50-50 blend. Basically, it takes 50% of the value from the image's color and it combines it with 50% of the value from the background's color. So we get kind of an averaging of the image and the background. Mode 1 is 100 and 100. Now, what's really the difference? What's the difference between these? Basically, in mode 0, it was averaging the numbers together. Mode 1 takes the value of the image and adds it to the background, what's called additive blend. You can see the difference between mode 0 and mode 1 is that mode 1 will just be kind of a brighter, lighter version, closer to white than mode 0, which is kind of like a darker version of mode 1. That's kind of the relationship that they have. Mode 2, you can see it's subtractive, which means it takes kind of the inverse of the image and it inverts it and then adds it to the background. So we end up with something like this. You can kind of notice that some PS1 games will use this to represent like burnt textures. Once you know that this exists, you kind of have an eye for it and you can kind of spot it in different games. And then mode 3 is like mode 1, but just more faint. So I like to call that weak additive. Now in the previous example, we found out that we were looking at the second color in this color palette. And we got the RGB values of 10, 7, and 4 for that color. If we want to convert this color to something that we can actually use in a different program, so these colors, because they're only 5-bit, they go from 0 to 31. But we're used to colors that go from 0 to 255, if you remember from the beginning of this video. So in order to convert this color space to the normal color space that we're all used to, like 8-bit color, 8-bit per component instead of 5-bit for a component, we just left shift these numbers by 3, which is equivalent to multiplying them by 8. And then we get the 8-bit values for this color. So for this brown, we take the individual components, we multiply them by 8 to get these values. And if we take these values and plug them into like a HTML color picker, we get the exact same shade of brown that we expected to find. When we're working with colors on the PS1, this is something that we'll basically always need to do when we're using different tools. So after the CLUT data comes the pixel data, the PXL data, which is the actual image data itself. Once again, it starts with one word that just tells us how big this section is, the data length. We call that bnum again. And then once again, we have frame buffer coordinates for where this image is going to end up in VRAM. After that, we have width and height again, and then the actual data. So very similar to the previous section. It's very similar because they are essentially the same thing. A color palette is just as much of an image as the actual image is. Now, one thing that you have to keep in mind is that this width value does not actually correspond to how wide the actual image is. It's how many basically pixels it takes up in VRAM. And those pixels are 16-bit wide. So when we were looking at the color palette, this width value actually did match up to the width of the color palette. But here it won't, because basically in 4-bit mode, 4 pixels can fit in the space of 1 pixel of VRAM, because a pixel of VRAM is 16 bits, but a pixel of the image is only 4 bits. So this number actually has to be multiplied by 4 to get the real width. So this tells us that we have a width of 8, but we know the image has a width of 32, so we multiply 8 by 4 to get 32. This is equivalent to how we see that the image is squished in VRAM horizontally, because it's working off of that same coordinate system basically. If this was an 8-bit image, the difference in coordinates would be times 2 basically. So we would double this image to get the real width if it was 8-bit. But if it's 4-bit, we quadruple it. And if it was a direct color image, then the number would actually be correct and we would not need to multiply it. So finally, we have the pixel entries themselves, the actual image data. Now here's a very unhelpful diagram of how the data is stored in indexed color mode. Basically, we know how it works though. We know that if it's in 4-bit mode, then the pixel entries are stored 4 bits at a time, one after another. And each 4 bits corresponds to 1 pixel. And in 8-bit mode, basically every byte is the value of a pixel. If the image is in direct color mode, the pixels themselves are going to be identical to color palette entries. So they'll contain the red, 5 bits of red, 5 bits of green, 5 bits of blue, and then the STP bit. And that is how each entry in the image, each pixel is going to be stored. So just like the color palettes. It also mentions 24-bit mode here. I'm not going to really talk about it because it's so rare to ever show up, but you can pause the video and look at that if you so desire. Now that we know how the format works, we can start to talk about what's wrong with the format, at least when it comes to us, when we're trying to reverse engineer it and when we're trying to extract images from a game. TIMs are not actually images. That's not how they're structured, and that's not really how they work. In truth, they're just like pre-packaged payloads that get loaded into VRAM, and at a point in the future, the game can interpret them as an image later, using possibly data and information that's not in the TIM itself. There are many different ways that the game can actually do this. One way is the STP bit. We talked about how the semi-transparency processing can be on or off, or it could be in different modes. But that's really only one way. There are actually more ways that a TIM can actually look different from how we expect it to. We'll talk more on it later. But for now, let's pretend that everything's going to work out just fine. Let's actually just extract the image. We can easily write a program, now that we know how the TIM format works, to extract a TIM. We know how to read the details from the header. We know how to read the height, the width, all the different offsets, and what mode the image is in. So we go to the start of the CLUT, and we can read the data into a color palette. And obviously we skip that step if there is no color palette, if it's in direct color mode. We know that we have to do this little trick where we multiply the RGB values by 8 to get 8-bit colors. And we know that actually, this is something that we didn't quite talk about before, but an image can have multiple color palettes. So if we really want to extract every possible image from a TIM, we would actually apply each and every color palette to that image. After we've processed the color palette, the CLUT, we can go to the pixel area and we can read out the data. The X and Y coordinates for each pixel we read is the pixel number modulo the width, and the Y coordinate is the pixel number integer division with the width. So that's how we get the XY coordinate if we're reading these pixels and we're trying to, put these pixels into an image. If the image is indexed with a color palette, then the values that we read for each pixel will be an entry in the color palette. So we use that as an index in the CLUT. But if it's direct color, we just use the color that we read directly from the pixel data. And we can extract an image that easily. That is the standard PS1 format taken care of. let's move on to the PS2 with Tim 2, the sequel. Gonna go through this one a little bit quicker since we kind of know how to deal with these file formats at this point. Tim 2 starts with a line that I like to call the Tim 2 line. It starts with the word Tim 2 in ASCII, and then the version number, which is always 4, and then something called the format, which we don't actually use, and then picture count, which is almost always going to be 1 from my experience, and then a bunch of empty space, which is not always empty. From my experience, games like to use this format byte kind of for their own nefarious purposes. Format kind of determines, in my experience, how big the header is going to actually be, but there's no real official documentation and there's no real pattern to how games will use it. You kind of have to work it out on a per game basis. And format determines also, I've seen how this empty space is used. You'll notice that a lot of the information for the PS2 and this specific format is a little bit more loosey-goosey because it's kind of pieced together from people who have reverse engineered it themselves. And so there's quite a few holes in how we understand this format, but they usually don't get in the way, so it's mostly okay. After the first line, we have the first part of the header. So we have first the total image size, which is actually the next 3 entries added up together. So we have the total palette size plus the pixel size plus the header size, and that adds up to total image size. After that, we have this entry that's called palette entry count. That usually corresponds to how many entries, how many colors are in a color palette per palette. So it's usually 100 when it comes to an 8-bit image, and 16 when it comes to a 4-bit image, and 0 when it comes to a direct color image, at least in my experience. Note that this total image size completely disregards the first line of this file for some reason. After that, we have color depth or something. Nobody really knows what this next byte represents. You can usually ignore it. After that, we have a bitmap count. If you look up what people know about it, they don't know. Nobody knows. It's usually unused. And in my experience, I've never seen it used. After that, we have the CLUP format. This is the actual format of the color entries themselves. So this is almost always going to be either 0 or 3 in my experience. Because colors on the PS2 are usually 4 bytes in length, it's going to be 3 if it's an actual paletted image, and 0 if it's a direct color image, at least in my experience. And then we have the pixel format, which is the actual format of the pixel entries themselves. These can either be usually 3, 4, or 5, because an image is either going to be direct color, which is 3, or 4 or 8-bit. It's just kind of how it goes. There's no real reason to use 16 or 24, at least from what I've seen, but I'm sure some games might use it. After that, we have the actual image width and height. And unlike on PS1, a TIM2 width and height actually do correspond to how large the image is, the actual dimensions of the image, regardless of the color mode. So these numbers are actually correct and you can rely on them. Now the next 4 entries are kinda unused. They're kinda weird and scary looking, but they're mostly irrelevant to our purposes. There is one that is relevant, and if you want to learn more about what these potentially mean, you can go to this link here where people have kind of reverse engineered the format itself and have put together some more detailed information on it. But a lot of it is still kind of undocumented. say we had this image right here, this Tim2 image, and it's 8 bits per pixel. So it has 256 colors in its CLUT, and there's 32 bits per color. Now we might expect that the color palette is stored sequentially. That is, for this example right here, it would be stored starting at top left, going across, and so on in the sequential order that we're used to. But that's not necessarily the case on PS2. In fact, it will most of the time almost always not be the case. So let's take a look at this CSM register, this color storage mode. Well, it tells us that there are two storage modes for colors, for color palettes. With CSM2, it says that it's stored sequentially, but the PS2 GPU uses the CLUT slower. So having the colors stored sequentially is actually bad. It's actually slow when it comes to how the GPU works. So this is almost never going to be how you see color palettes on the PS2. What you will see is color storage mode 1, where the colors are stored and swizzled every 20 bytes, every 32 bytes. This option is faster. Well, the key word here is swizzled. What does that mean? Here's exactly how that works. So it said it was swizzled every 32 bytes. Well, 32 bytes, when each color is 4 bytes, corresponds to 8 colors. So we're going to call every stretch of 8 colors a block. And when we're storing blocks, every second and third block is going to be swapped. So when we count, when we go through the color palette, and we say that this is the first color, and this is the first entry in the color palette, and this is the second, third, fourth, and so on. After we get to the 8th, and we're looking at for the 9th color, we don't go to the next color sequentially. We actually skip this entire block and go down to block 2, which is down here. Which is down here now instead of where we would expect it. And then after the colors in block 2, the 17th color is going to be all the way back. We have to go backwards to the start of block 3. And after we finish block 3, the 25th color is going to be at the start of block 4, which is after block 2. And this pattern repeats over and over again with every second and third block being swapped. So instead of 1, 2, 3, 4, it goes 1, 3, 2, 4. This is almost always how colors in the color palette will be stored. So we said before that the red, green, and blue colors, the color components on PS2 go from 0 to 255. Well, they don't actually do that though. Well, they do with the red, green, and blue values, but the alpha channel only goes from 0 to 128 for some reason. So a value of 80 for which corresponds to 128 for a color is actually fully opaque. Now, why does it do this? I can only imagine that because it's an optimization kind of thing. Because if it goes from 0 to 80, we can easily check if a color is full opacity by checking one single bit. If you look at the actual bitwise representation of 128. So maybe it's a little fun little optimization that they do. So how do we extract a Tim2 image now that we know how the format works? Well, it's almost going to be exactly how we extract a Tim1 image. It's really, we follow the exact same steps. We read the details from the header, then we read the color palettes, then we read the pixel data, and we output the pixels to an image. I'm not going to go over the actual code involved here because you should be able to write a program like that in your own language, in your own programming language. So this is just really pseudocode to get you started, to point you in the right direction. I didn't say it would be part of the video, but let's talk a little bit about how to inject an image, how to modify an image. The process at this point is actually really easy. We just reverse the process that we use to extract the image. If it's a direct color image, we step through each pixel and we just output a different color corresponding to whatever image that we're replacing it with. If we're on the PS1, we need to remember to convert the 8-bit colors back into 5-bit color components. Now, if we're injecting a paletted image, all we have to do is we don't output the colors directly, of course. So we go to each pixel and we output the index of the closest color that matches the modified color of our image. How we find the closest color to a color in a color palette is we use sum of squares. So we take the difference between the red component, the blue component, the green component, and the alpha component, and we take the squares of that value and we add them together. And we do that for each color in the color palette. Then we choose the one that has the lowest value, and that gives us the closest color in the color palette. We always need to watch out though for 100% transparent colors. A lot of programs like Photoshop like to give very strange values to colors that are 100% transparent. They won't always use 0000. They might use something like 255, 255, 255, 0, which is 100% transparent, but white, which is not really different from 100% transparent, but black. But you will get a very different value if you use that with the sum of squares technique. So you have to watch out for that. It might be tempting to say, hey, why not just change the color palette to better match the modified image? I think that in general, you should try to avoid that if you can. The reason is because on these systems, images can share color palettes. So if you modify the color palette of one image, you might actually change a completely different unrelated image that was using the same palette. So you have to watch out for things like that. But let's say that you absolutely had to modify the color palette. In that case, I suggest using an actual image library that can handle quantizing an image. Quantizing just means basically reducing the number of colors in an intelligent way to a certain number, and then using the color palette that it gives you. So here in this example, this is the Python image class, and this is how you use the quantize function to give you a quantized image. You can specify the number of colors that you need, and then you can use the you can use the color palette that it'll spit out after doing that. Quantizing is reducing the color space. So if you quantize this image here, you get this much lower quality image that has fewer colors in it. Now, the reason that we don't want to create the color palette ourselves and we want to use a library that handles quantization is because the math involved is actually very, very, very difficult and strange and relies on actually a bunch of different very heady concepts, such as how the human eye actually perceives color in order to find the absolute best set of colors in a color palette that will represent an image. So it's not something that we want to get into. We just want to use a library that will take care of it for us. But hold on, wait. Why did we just spend all that time learning how TIM 1 and 2 works? Didn't we already say that there are programs that can extract TIM 1 and 2 images, and that most games will actually not even use TIM 1 or TIM 2 at all? Why did we go through all that effort? Well, to learn why a certain programmer working on a video game might choose not to use TIM or TIM 2, we had to kind of learn how they work first. So why would programmers create their own format versus using TIM 1 or TIM 2? Now, I mentioned it before, but there are actually many shortcomings to the TIM format. There are reasons why a game might want to choose not to use it. So one, perhaps they don't like how there's a static relationship between color palettes and images. We saw that, every TIM contains color palettes and it contains images, but it kind of bundles them together. a game might not like the fact that they are bundled together. A game might have a more dynamic relationship between color palettes and images that Tim doesn't really allow. There's also, as you saw, a whole bunch of unnecessary information in the header. Now that might not matter too much for a game that has very large images, but what if a game is using many small images, and each image had its own big unnecessary header? Well, that would take up a lot of additional space that would just be dead weight. Remember how we said that the VRAM destinations were baked right into the TIM? Well, that could also be a shortcoming. I mean, what if a game wants to have a dynamic loading of images into VRAM? Well, TIM doesn't really allow that. TIM is very baked in from the start. So a game that does dynamic loading wouldn't really be able to use TIMs very well. We saw this early on, but there was something called mixed image formats that the TIM format just kind of mentioned, but didn't really explain at all. Well, it doesn't actually handle that very well. TIM kind of assumes that the entire image is in one format and not mixed together. Well, there are reasons why a game might want to use images that have mixed image formats, possibly to fit together better into VRAM, but TIMs don't really support that very well. TIMs also only support rectangular image storage. It doesn't really support swizzling. Now, this is a different kind of swizzling than what we saw before. But basically, you can swizzle an image in order to optimize the amount of space it takes up. And we'll see that later. But TIMs only support rectangular images, as we saw before, so it wouldn't really work for TIMs. Also, TIMs and TIM2s are really easy for hackers and possibly even competitors to rip assets out of your game. It makes you an easy target. So that's also a consideration when programming a video game. There are also just any number of features that a programmer can come up with that TIM doesn't support. It's really up to the programmer at the end of the day how they want to handle how they load their graphics, and they might have just a better idea for how to load graphics than what TIM is. So how do we rip a graphic whose format we don't know anything about? Well, we have some clues. Most image formats will basically take elements of how TIM and TIM2 works and just sort of make changes to it, or just kind of take elements of it. That's pretty common, actually. So we know that to render an image, we need either the pixel data and the color palette, or just the pixel data if it's a direct color image. Programmers will just find different ways of packaging these elements together: the pixel data, the color palettes, and the metadata, the details in the header. They'll just package them together differently. But if we know what they're trying to do, we can figure out how their image formats work. And we can use techniques that are just a bit better than just staring at numbers in a hex editor.
I thought that if I stared at these number blocks long enough, then I would begin to see some kind of pattern. So far, nothing.
Because the pixel sections in PS1 and PS2 games are stored linearly, we can actually use any number of data visualization tools and scrub through their game files that we suspect have image data. So here's a file that I think could be an image, and I have it open in a hex editor. The name of this hex editor is 010. Now, it is a paid piece of software, but there are free alternatives that I'll show you in a bit. Now, if we think this file might contain an image, it's as easy as expanding the visualization window until we see something. So take a look at this.
Pattern match found.
Specify.
The number blocks are mathematical representations of
PlayStation graphics. And there you have it. It's just that easy. This file does indeed contain this image. We can find out the dimensions of this image by selecting sections of it and seeing just how wide, how much area, how many bytes we need to select in order to get one line of data highlighted. We can compare that to the total size of the file to get the width and the height. Now, if we don't want to use a program that costs money, we can use a program called Tile Molester. This is a program that lets us visualize data, and it does it in a quite more powerful way. So we have this file that we suspect of being a graphic. The first thing we need to do is go into mode and set it to 2-dimensional. And then we can give it a color mode that we suspect that it might be using. This is from a PS1 game, so we selected RGB 555, which is the 15 or 16-bit color mode that we know and love. After that, all we have to do is modify the dimensions, and if it is indeed an image in that color mode, it should appear just like this. Very, very clean example of it. Now that was a direct color example, but what if we have an indexed color mode? Well, we can handle that in Tile Molester as well. Once again, we'll set the mode to 2-dimensional. Then we'll set the codec to something like 8-bit or 4-bit. After that, we can still modify the dimensions and see if we get an image showing up. And if it is, then we should be able to eventually see some kind of image like this. But as you'll see, the colors are not correct. But we can fix that. If we go to Palette and then import from this file, first we make sure that the format is in 15 BPP BGR. And then if we know exactly where the color palette is in this file, all we have to do is give it that offset and a size that is at least the size of the color palette in bytes. And if we do that correctly, the colors should appear correctly. Now in this case, these colors are not perfectly correct. This program doesn't necessarily actually handle them perfectly. It's just a limitation of the program itself, but it's close enough, and it gives us a pretty good idea of what the image should look like, at least. That's all well and good, but that doesn't work for identifying CLUT sections. Well, thankfully, CLUTs have very distinct properties that we can use to identify them. On the PS2, we know that they're generally going to be 4 bytes per color, and the 4th byte for each color is going to usually be 80 because it's usually going to be fully opaque. And the total file size of a CLUT is going to be either 40 or 400, depending on whether it's 4-bit or 8-bit. So we can use those details to kind of identify an image CLUT. On the PS1, we have 2 bytes per color. We know that the highest bit will tend to be 1 because of the STP bit. And we know that the total CLUT size is going to be either 20 or 200 in hex. So here we have an example that's very easy to tell that this is a color palette. Why? Because color palettes tend to start and end with either pure white, pure black, or pure transparent, and that corresponds to either 8000, FFFF, or 0000. So this is actually 3 color palettes stacked together, and each of them starts with FFFF and ends with 8000. So it's very telling that this is a color palette. So here are some actual examples of non-TIM image formats. Kowloon's Gate is a PS1 game, and the way this game stores pixel and CLUT sections is basically with 0 metadata at all. There is 0 header going on here. It just stores the images, the pixel sections as is, and color palettes as is in different locations. We can extract these images because we can identify the pixel data as well as the color palette data, as we said before. The color palette data was luckily stored pretty close to the individual images. You will usually find images very, very close by with their color palettes. That's generally how it is. So here's another example. This is Made and Machine Gun on PS2. It had a format that it called text. And in the header, there's only a little bit of information that we needed to figure out. Basically, it had an identifier that let us know that this was a texture image, that this was a graphic. After that, there's a bunch of unnecessary information, and then there's the end of the CLUT. That's actually useful because the CLUT would always start at the same location. It would always start here at A0. And then we could use this value as the endpoint for the CLUT. And then after the CLUT is another header block, the header for the pixel data. And in this block, the part that we only care about is this width and height here. So this 100 width and 100 height right here. After a fixed size for the header, there is the actual pixel data. And that is all the information we need to extract these images, because this game kind of gets a little bit lazy, and every single image in this game is the same color depth. They're all 8-bit, and they only have one color palette per pixel, per pixel. So it was very easy to extract the data at that point. The reason we're able to identify these sections of the headers is because we just have that experience of going through TIM and TIM2, and we know what kind of information to expect in these headers, because we know we know what's required for the game to render an image. So that experience helps us identify different parts of metadata, different bits of metadata. So here's an example of a game that actually uses TIMs, but it uses it in a very non-standard way. This is Harmful Park, game for the PS1 that I translated. As you can see, the game has very detailed sprite animations, but looking at just the TIMs themselves, it's not exactly clear or easy how to piece them together to make the actual complete animation. In order to interpret the data from the TIMs, it uses something called an ANI file, and the way they work is a bit complicated. And when I say a bit complicated, I mean a lot complicated. I won't go through the entire thing, but there is quite a bit of data that the animation files reference and specify, and putting it all together was a big hassle. But I had to do it because text itself was being stored in this format. And if I wanted to translate the game from Japanese to English, I had to figure out this format. So here's the Cliff Notes version of it. The ANI files specify sprite animation basically by slicing up parts of TIMs and stitching them together in sequence. So each slice of an image can have its own color palette, rotation, XY scaling, positioning, color depth, transparency processing, etc., etc. But here's the tricky part, is that all pixel and CLUT references are made to VRAM coordinates and not TIM files. Here are a bunch of examples of animations that I've pulled from the game. You'll notice these little red numbers. I put them at the top left of each slice of an image, basically, to visualize kind of how these images are being put together. So why is that a problem, that the animation files reference VRAM coordinates only? Well, it's that we can't necessarily really know when we're extracting the animations what's exactly in VRAM. Well, luckily enough, the game was structured in such a way that all of the relevant files were in the same folder together. So an animation file and all of the relevant TIMs for that animation file were in the same folder together. So we knew what was in VRAM because what was in VRAM were these TIMs. So how do we extract an animation? First, we have to build a simulation of VRAM, basically. We have to build that buffer. Then we load each TIM into that buffer. And then when reading the animation, we can slice off each of the little bits, the components of, pixel data and CLUT data to build each frame of the animation in sequence. Here's a little visualization of the entire process. First, we have a TIM image, and we load that TIM image into our VRAM buffer. And then from that VRAM buffer, we read the animation data. And the animation data gets spit out like this. And then from that animation data and from the VRAM that we have to reference it with, we can extract each frame of an animation as specified in the ANI file. Something that I haven't talked about yet are VRAM texture pages. See, actually VRAM is divided into these sections, and as you can see, graphics in each section do not cross these boundaries. There are 32 little rectangular sections, and images are not really allowed to cross that boundary. The reason why this is the case is kind of complicated, but when the GPU is working on a specific texture page, it can't really reference other texture pages at the same time. This turned out to actually be a problem for me when I was translating the game because I kept trying to load, different text images from different texture pages, and it just didn't work at all. And I couldn't really figure out why until I saw this basically diagram about how texture pages work. The GPU can only really work on one texture page at a time. If you really want to get into the nitty-gritty of how a scene is being rendered on PS1, you can check out the GPU bugger in No Cache PSX. This is a very, very helpful and very, very cool tool that actually breaks down each frame of the game's video output as a sequence of GPU commands, and you can actually step through each GPU command and see what's being output. For example, the GPU call that is rendering this character on screen is this command right here, this 24x24 text blend. And the exact instructions that are sent to the GPU you can see right here. And from these instructions, you can actually extract data on how the game is rendering this image. For example, this is a 24x24 sized image, and you could see that the final line of the GPU instruction is 18 and then 18. Well, 18 is in hex is 24. So you can get the dimensions of the call from here. Also in here are probably the UV coordinates of the texture within this texture page. You can see that it has a handy representation of which texture page is being looked at and which color palette is being applied to it. So it's a very, very handy, very, very neat tool to step through and see how this image, this frame of the video output is being rendered. And if you really want to go all the way, you could attempt to decompile the game. And this is something that takes a lot of work. It's something that I have to do for text rendering routines in the games that I work on usually, to change how to figure out how text is being rendered exactly and how I can change that to better suit English text. For example, here is the text rendering routine in Blue Legend of Water. And, from this, if you can get to this point, you can do basically anything when it comes to learning how a game renders images and using that knowledge to extract images. This is much too complicated to get into in this video, though. That'll have to be maybe some other time. Now let me talk about the absolute worst case scenario that I've ever come across on a video game that I was trying to translate. These are images in Racing Lagoon. And first of all, these images are not rectangular. Instead, they're a sequence of small squares that are sometimes out of order Sometimes they have different color palettes in different parts of the image. Sometimes they mix up color depths within the same image. So parts of it will be 4-bit and parts of it will be 8-bit, kind of randomly. They'll have gaps that are filled by blank colors, which complicates things even further. And on top of that, all of these things we could deal with if we could just read the information from the header and figure things out that way. But these images had no header, they had no metadata. So it was a complete nightmare. This is how the image format actually works. Say we had this image right here of this character. Well, how the game would store this image is it would break it down to a grid of squares, and squares that contain image data would start at the top left and go down, and every square, red square in this case, that I've highlighted that contains image data, it would store individually. So it would store this square, and then it would store the next one, and then the next one, and then it'll go down the next column, and it would store those squares, and so on and so forth. And if it encountered a square that was an entire solid color, it would just skip it. It would also skip squares that are reused within the same image. So it's basically a complete nightmare. For some of the images, I was able to kind of trick the game into displaying properly. For example, here I've set the image height to be of a certain height, and from there are different parts of the image, just parts of it, that would render normally when extracted. And I would call that section right there the eye of the storm, since everything else was a mess. But in this little section right here, for this little text that I wanted to translate, I could at least get that part to look normal, and I could edit it normally. But that didn't work for everything, because at the end of the game, literally the very final scene of Racing Lagoon has a whole bunch of these graphics as text. And what I came up with to translate that text is I didn't even bother extracting it correctly. What I did was I just replaced every single square with a code. So for example, this square was M3 and then M6 and so on and so forth. You can see it kind of goes down top to bottom. So 3, 4, 5, 6, 7, 8, 9, and so on and so forth. And then what I would do is I would look at where these codes ended up on screen. And then I would just write in the text into those squares with the right text corresponding to a line of codes. So for example, I have a line of text here, and then below that I have a line of codes where I wanted that text to go. And by doing that, I was able to finally insert the text. It was very, very tedious. It was very, very difficult. I had to come up with multiple different solutions within Photoshop and how the images were being extracted in different formats. You could see that actually some of these M's become pluses at some point. The parts that are pluses are actually a different color depth and use different color palettes from the parts that are M's. And it was just all a huge, annoying mess. But in the end, I figured it out and came to an at least acceptable solution. So that brings us to the end of the video. Now, it's absolutely impossible for me to cover everything that there is when it comes to extracting images. But what I really genuinely want to learn is what you took away from this video and what you still might have questions about. So if you have any questions about how to extract images, and especially if you've tried to extract an image from a game and had trouble, please let me know, either in the comments below, or you can message me on Twitter. I might make a follow-up in the form of either a video or a stream where I try to answer some of the questions, because I'm sure people are going to have questions based on this video, because I'm sure there are elements that I didn't explain fully properly. But I would love to hear what people have encountered themselves when trying to rip images. So please, if you have any comments, please get them to me. And as always, I want to extend my deepest thanks to the people who support me on Patreon. These videos would not exist without them.